Welcome to today's deep dive. It's Tuesday, March 3, 2026, and today we're looking at a really fascinating piece of history.
Yeah, one that highlights a massive contradiction in how we think about design and engineering.
Exactly. Let's start by just setting the scene for you. It's November 10th, 1943, and we are standing on the tarmac at Rechlin.
Which was essentially Germany's premier, highly classified military aviation testing facility during World War II.
Right. So, walking across that tarmac is Germany's chief test pilot. He's approaching a captured American fighter plane, a P-47 Thunderbolt.
And we should note, the other German pilots have been openly mocking this plane.
Oh, relentlessly. They've nicknamed it the flying milk bottle because of its massive, bulky shape.
Right, the expectation, based on German intelligence and, frankly, their engineering pride, is that this American machine is going to be crude, heavy, and completely unsophisticated.
But when this pilot actually evaluates the aircraft, he uncovers a fundamental engineering reality that foreshadows the outcome of the entire conflict.
It really is a brilliant case study. Our source material today comes from a highly detailed breakdown by the Tales of Valor podcast.
Yeah, so our mission today is to examine the experiences of that test pilot, Hans-Werner Lerche, and his evaluation of the P-47.
But looking at the broader picture, this is really an exploration of two completely opposed design philosophies.
You have the German approach, which was intensely focused on individual excellence and peak performance.
Clashing directly with the American engineering approach, which prioritized industrial and operational sustainability.
And for anyone listening right now who designs systems, or maybe you manage a team or run a business, the mechanics of this clash offer a complete masterclass in systems thinking.
It forces us to ask whether we should be building highly tuned masterpieces or forgiving, resilient workhorses.
Let's start with the evaluator himself because, his background gives a lot of weight to what he eventually concludes.
Oh, absolutely. Hans-Werner Lerche wasn't just some guy who happened to fly planes.
No, he was arguably one of the most uniquely qualified aviation evaluators of the 20th century. By 1939, he was the chief test pilot at Rechlin.
And he had a formal background in aeronautical engineering.
Right. And over the course of his career, his logbook recorded flights in over 120 different aircraft types.
Which is staggering. We're talking prototypes, standard production models, and just a massive array of captured enemy aircraft.
Yeah, that engineering background is key here. It meant Lerche evaluated aircraft objectively.
Right, based on data and mechanical reality rather than ideology. He was known for writing technical reports that were just brutally honest.
If a new German prototype had a fatal flaw in its aerodynamics, he documented it.
If an enemy plane had a superior hydraulic system, he noted it.
And that kind of unvarnished truth was not always welcome among high-ranking Nazi officials.
No, they vastly preferred blind optimism about their own superiority.
Yeah, but because his technical insights were so critical for the war effort, his evaluations carried an enormous amount of weight.
Even if the leadership didn't really like what he had to say.
Which brings us to how the specific American plane ended up on his tarmac in the first place. Because the backstory is genuinely intense.
It really is.
So the P-47 sitting at Rechlin was nicknamed Beetle, and it had been captured just 3 days prior on November 7th, 1943.
Right, an American pilot, Lieutenant William Roach, was flying an escort mission over Europe.
And he gets completely lost in this massive weather system. His flight group is scattered, his fuel gauge is dropping dangerously close to empty.
And then Roach spots an airfield through the clouds.
Yeah, assuming he's managed to cross the English Channel and is looking at southern England, he lands the plane.
Follows a ground vehicle to a parking area, cuts the engine.
And only then does he realize he is sitting in the middle of a Luftwaffe base in Caen, France.
I mean, it's a catastrophic navigational error.
German troops immediately surround the aircraft, take Roach prisoner, but for the Luftwaffe, this is a huge deal.
Oh, capturing a completely intact, fully operational late-model American fighter that was an intelligence goldmine.
And they moved incredibly fast to secure it. They knew if Allied reconnaissance spotted the missing plane sitting there, Allied fighters would be sent immediately to strafe and destroy it on the ground.
Right, so they flew it inland to Rechlin and quickly repainted it in German camouflage.
They assigned it the code T9 plus FK, which designated it as part of the Zircus Rosarius.
Right.
I want to pause on that term, actually, because it's a fascinating detail in the source material. What exactly was the Zircus Rosarius?
So it was essentially a highly classified, specialized Luftwaffe squadron. Their entire operational purpose was to fly captured Allied aircraft.
So Spitfires, Mustangs, Thunderbolts.
Exactly. And take them on tour to different German fighter bases. They would stage mock dogfights against regular German pilots.
To kind of let the frontline German pilots see the enemy aircraft up close.
Right. Understand their flight characteristics, figure out their mechanical blind spots before they had to face them in actual lethal combat.
Okay, let's unpack this, because that makes the pre-existing bias against the P-47 even more interesting.
It does.
Before Lerche even inspects it, the German fighter pilots have largely dismissed it.
Because they were accustomed to their own designs, like the Messerschmitt Bf 19 and the Focke-Wulf Feldwebel 190.
And those aircraft were sleek, they were angular, they were designed to look like precision weapons.
Whereas the P-47 was built around a massive radial engine. It gave it a fuselage shaped almost like a giant barrel.
Right. The German perspective was that the Americans didn't know how to build refined aerodynamics, so they just bolted the biggest engine they could find onto a heavy, unrefined airframe.
And that bias stems directly from their core engineering philosophy.
Mm-hmm.
The German approach to fighter design prioritized ultimate agility, climb rate, and top speed above almost everything else.
So when they looked at the P-47's massive 7-ton bulk, they viewed it as a sledgehammer.
They assumed it was a product of crude, unskilled manufacturing from a country they frankly considered culturally inferior in terms of high-end engineering.
But Lerche, being an objective engineer, didn't rely on hangar gossip.
No, his job was to conduct a systematic teardown of the machine.
He starts with a physical walk-around of the exterior, and this is where the first cracks in the German assumptions start to appear.
Right. As Lerche gets close to the airframe, he isn't seeing the crude manufacturing his peers joked about.
No, he's noting the flush riveting. He's looking at incredibly clean welds and highly precise panel gaps.
The source material specifically notes he was struck by the high-grade alloys being used consistently throughout the entire structure.
The mechanical reality he's observing here is the difference between bespoke craftsmanship and sophisticated mass production.
Exactly. Lerche realizes the P-47 wasn't crude at all. It was built to incredibly tight manufacturing tolerances.
And more importantly, it was designed so those tolerances could be replicated thousands of times over on an assembly line.
Which was a stark contrast to what was happening in German factories at the time.
I'd imagine the German factories in late 1943 were operating under entirely different pressures than American factories in places like New York or Indiana.
Oh, entirely different. German manufacturing was being actively dismantled by Allied strategic bombing campaigns.
Supply chains for high-grade metals were failing.
Furthermore, the German war machine relied heavily on forced labor in their factories.
Which inherently leads to passive sabotage and just a massive drop in baseline quality control.
Right, so German engineers might design a beautiful precision aircraft on paper, but the actual planes rolling off the line were becoming increasingly inconsistent.
Some were perfect, others had engine flaws or misaligned panels.
What Lerche is looking at with the P-47 is a machine that proves the American industrial base is operating without those disruptions.
They're producing complex machinery with uniform consistency.
Exactly.
The contrast becomes even sharper when Lerche actually climbs up onto the wing and gets into the cockpit.
The ergonomics of this era of aviation are fascinating.
They really are. In the primary German fighter, the Bf 109, the cockpit was notoriously cramped.
It was designed to have the absolute minimum aerodynamic footprint.
Right, so for a pilot like Lerche, it meant his shoulders were literally rubbing the sides. The canopy was so low, he had to constantly hunch over to avoid hitting his head.
It was physically exhausting to sit in for more than an hour.
Which goes back to their philosophy of peak performance.
What's fascinating here is that the German engineers viewed pilot comfort as completely secondary to aerodynamics.
If cramming the pilot into a tiny box reduced drag and gave the plane a slightly higher top speed, that was considered an acceptable systems trade-off.
They accepted pilot fatigue as the cost of doing business.
But the P-47 takes the exact opposite approach. Lerche drops into the seat, and it's massive.
It's heavily padded.
There is room to move his arms, stretch his legs. The canopy is this large bubble that gives him incredible visibility without having to crouch.
Right.
I do have to ask, though, doesn't making a larger cockpit inherently increase the drag and make the plane an easier target?
It does increase drag and structural weight, yes. But here we see the American philosophy of systems thinking extending beyond the machine and including the human operator.
Because American planners knew their fighters were going to be flying bomber escort missions deep into Germany.
And those missions could last up to 8 hours. If a pilot is crammed in a freezing, vibrating tiny box for 7 hours.
By the time they actually encounter enemy fighters, they are physically degraded and mentally exhausted.
Exactly. The American engineers determined that a comfortable, alert pilot flying a slightly larger plane is much more lethal than an exhausted pilot flying a perfectly aerodynamic plane.
The comfort wasn't a luxury feature.
No, it was a deliberate operational requirement to ensure combat effectiveness at the end of a long mission.
That human-centric design goes even further when Lerche starts examining the instrument panel.
The notes here on the gauge design are incredible to think about in the context of 1943.
Yeah, in German aircraft, the instrument panels were essentially a wall of complex dials with raw numbers.
To fly safely, a German pilot had to memorize the specific operating limits, the exact temperature threshold, the exact manifold pressures.
But on the P-47, Lerche finds that the Americans have painted color-coded bands directly onto the glass of the gauges.
Green sections indicating normal operation and red sections indicating danger.
It's a brilliant example of what we now call inclusive design.
It really is, and it speaks to how American engineers anticipated the entire life cycle of the aircraft.
German manuals assumed the end user was an expert.
Right. Early in the war, the Luftwaffe had elite training programs, so relying on memorization worked.
But American engineers were designing planes for a massive, rapidly expanding wartime military.
They knew the pilot in that seat might be a 19-year-old kid from Ohio with only a few dozen hours of flight time.
Or a free French pilot, or a Polish exile flying for the RAF who might not even speak fluent English.
The color-coded gauges assumed pilot ignorance. You didn't need to know the exact numerical limit of the oil pressure.
You just needed to know that if the needle was in the green, the plane was safe.
It reduced the cognitive load on the operator entirely.
So Lerche completes his pre-flight checks, which are obviously simplified by this design, and he fires up the engine.
The P-47 is powered by a Pratt Whitney R2800 double-wasp radial engine.
It roars to life, and Lerche notes how incredibly smooth it is.
It idles perfectly without the rough spots or intense vibrations that were becoming common in late-war German engines.
Right, due to those manufacturing inconsistencies we talked about earlier.
Exactly.
But before he even gets it into the air, he has to taxi this 7-ton machine to the runway, which brings up a major mechanical difference in the landing gear.
Ground handling of aircraft is an often overlooked metric of military success. Let's look at the mechanics of the German Bf 109.
Okay.
To save weight in the wings, its landing gear was attached directly to the fuselage and folded outward.
Meaning the wheels were very close together.
Right. That narrow stance gave the aircraft a high center of gravity, making it incredibly unstable on the ground.
When landing or taking off, the massive torque of the engine could easily cause the plane to violently spin out of control.
A mechanical failure known as a ground loop.
It was notorious for breaking landing gear and destroying wings before the pilot ever even saw combat.
But the P-47 utilized a completely different geometric approach.
Its landing gear was attached far out on the wings and folded inward.
This gave the aircraft a very wide stance, distributing that massive weight over a larger area and significantly lowering the center of gravity.
Lerche actually records a specific anecdote about this in his evaluation. During his taxi run, he made a procedural error.
He forgot to engage the mechanism that locks the rear tail wheel into a straight position.
And on a massive, powerful aircraft, a free-spinning tail wheel during acceleration is a recipe for an immediate disastrous ground loop.
In a Bf 109, that error would almost certainly have resulted in the plane snapping sideways, collapsing the gear, and ending the test flight right there.
But Lerche notes that the wide stance and the robust mechanical design of the P-47 made it incredibly forgiving.
Even as the plane started to veer out of control, the wide center of gravity allowed him to physically muscle the aircraft back into a straight line and save the plane.
The design absorbed his mistake and allowed the mission to continue.
It's incredible.
Once he finally gets it off the ground, the flight characteristics are a mixed bag, but they reveal a specific strategic purpose.
Lerche puts it through its paces. He notes that down low, it is not an agile dogfighter.
Right, it doesn't have the instantaneous turn radius of a Focke-Wulf.
But it is remarkably stable. And when he pushes the throttle and climbs past 15,000 feet, something shifts.
The P-47 utilizes a massive turbo supercharger system, which gives it an undeniable advantage.
The mechanics of the supercharger are crucial to understanding the air war over Europe.
As an aircraft climbs to high altitudes, the air becomes incredibly thin.
Internal combustion engines need oxygen to mix with fuel to create power. In thin air, Naturally aspirated engines, or engines with basic superchargers, begin to suffocate, and their power output drops significantly.
But the American turbo supercharger solved this by taking the hot, expanding exhaust gases from the engine and using them to spin a turbine.
That turbine then forced massive amounts of compressed outside air back into the engine.
It mechanically allowed the massive Pratt Whitney engine to breathe sea-level air even when it was flying at 30,000 feet.
So while the German interceptors are struggling to maintain power in the thin air, fighting to get high enough to attack the bombers.
The P-47 is operating at peak efficiency. Lerche flies the plane for 90 minutes.
He tests the dive speed, which is terrifyingly fast because of the sheer weight of the aircraft.
And he tests the hydraulic systems, which remain perfectly responsive.
He experiences a profound shift in perspective during this flight.
He realizes this machine wasn't designed to win a one-on-one turning fight at low altitude.
If we connect this to the bigger picture, he recognizes the broader systems engineering at play.
The German philosophy was to build the ultimate fighter, a plane designed for the specific 5-minute window of aerial combat.
The American philosophy was to build the ultimate operational system. The engineers who designed the P-47 didn't just design for the dogfight.
They anticipated the entire life cycle of the machine.
They assumed it would be disassembled, shipped across an ocean in wooden crates, reassembled by mechanics in a muddy English field.
Left out in the rain, flown by a tired novice, filled with low-grade fuel if necessary, and shot full of holes.
And it was designed to survive all of that and still perform its mission.
So Lerche lands the aircraft, taxis back to the hangar, and shuts down the engine.
The German ground crew and other pilots are waiting, likely expecting him to tear into the crude design of this flying milk bottle.
Instead, he climbs out and delivers a verdict that completely shocks them.
He states that it is the best designed operational fighter he has ever flown.
That evening, he sits down to write his official technical evaluation, and this document really serves as the core takeaway of our deep dive.
He breaks down the speed, the supercharger, and the handling. But in his strategic summary, he clearly outlines the clash of philosophies we've been discussing.
He essentially drafts a warning to the German high command.
He writes that Germany is building weapons for individual excellence.
Their system requires an unbroken chain of perfection. Perfect manufacturing, pristine airfields, expert mechanics, and elite pilots.
If any link in that chain breaks, the weapon fails.
America, he observes, is building weapons for industrial war.
They're building forgiving, rugged machines that can absorb the friction, errors, and chaos of a massive, protracted conflict.
He officially recommends that German aviation design needs to abandon its obsession with peak performance and immediately prioritize operational reliability and ease of maintenance.
But his report hits a massive bureaucratic wall.
The Nazi high command receives the evaluation, and it completely contradicts their ideological worldview.
The state propaganda mandated that German engineering was culturally and intellectually superior.
So rather than addressing the mechanical realities Lerche presented, leadership categorized his report as overly pessimistic.
Some even suggested that flying the American plane had simply demoralized him and clouded his judgment.
They filed the report away and ignored the recommendations.
It's a textbook example of leadership ignoring data because it conflicts with a preferred narrative.
But the grim realities of industrial war are mathematical, and they can't be ignored for long.
Within months of Lerche's report being filed away, the skies over Germany were filled with swarms of P-47 Thunderbolts, escorting bombers and ravaging the supply lines.
The statistics from 1944 onward really illustrate the devastating nature of the American approach.
The United States produced over 15,600 P-47s during the war.
To put that manufacturing consistency into perspective, at the peak of the industrial effort, a brand new Thunderbolt was rolling off the assembly line every single hour.
By comparison, Germany produced roughly 36,000 single-engine fighters total across the entire war.
On paper, that sounds like the Germans had a numerical advantage.
But the reality in the field was entirely different.
And that reality comes down to the math of operational availability.
Because the American planes were robust, easy to maintain, and utilize standardized parts, an American squadron with 100 planes might have 85 to 90 of them ready for combat on any given morning.
The German squadrons, burdened by temperamental engines, fragile landing gear, and a lack of spare parts, might only have 60 planes available out of 100.
The rest were grounded for complex repairs.
When you multiply superior production numbers by vastly higher daily availability rates, The result is overwhelming numerical superiority at the actual point of contact in the sky.
It didn't matter if a German pilot in a Bf 109 had a slightly better turn radius if he was constantly facing 4 or 5 Thunderbolts that were always fueled, always functioning, and always in the air.
This entire dynamic is validated after the war ends. Lerche miraculously survives the conflict without a single crash.
He is eventually detained and interrogated by Allied technical intelligence officers who had uncovered his old reports.
The Allied officers were fascinated by his evaluations. They basically asked him to clarify his stance. Was he saying the American aircraft were mechanically superior in their performance?
Lerche corrects them. He explains that the critical advantage wasn't speed or agility. The advantage was that the American design allowed for sustained operations.
The robust engineering meant more planes flew more sorties.
The inclusive design of the cockpits meant rookie pilots could be trained faster and survive longer.
Every piece of the machine was optimized not for a single moment of glory, but for the grueling marathon of a global war.
Exactly.
So what does this all mean for you listening today?
While the context of this story is military history, the underlying principles of systems design apply everywhere.
Whether you are coding software, designing a supply chain, or structuring a team, you face the same choice Lerche observed on that tarmac in 1943.
You have to decide if you are designing for peak performance under perfect conditions, or if you are designing for operational reliability in the real world.
The lesson of the P-47 is that a system that reliably operates at 80% capacity through chaos, user error, and degraded conditions is infinitely more valuable than a fragile masterpiece that requires 100% perfection just to function.
That concept forces us to look critically at our modern environment. We live in a culture deeply obsessed with optimization.
We constantly try to strip away redundancies to maximize efficiency in our businesses, our technologies, and even our daily routines.
We want everything to run as sleekly and fast as possible. But looking at the fate of those highly optimized German fighters, it begs a lingering question.
In our relentless pursuit of peak performance and hyper-efficiency, are we actually engineering the resilience out of our systems?
If your optimized system requires perfect conditions to survive, you haven't built a masterpiece. You've just built something that is waiting to shatter the moment it encounters the unpredictable friction of the real world.
That is a phenomenal lens through which to view the systems we interact with every day. Thank you for joining us on this deep dive into the engineering philosophies of the Second World War. Keep examining the design of the world around you, and we will catch you on the next deep dive.